Hello, today we're going to finish the turning points topic by going over length contraction and relativistic mass. By the end of today's lesson, you should be able to calculate the length contraction of an object in an inertial frame. You should be able to calculate the relativistic mass of an object and explain why no body with mass can move at speed c. And finally, you should be able to explain Bertozzi's experimental verification of relativistic mass. Recalling the last lesson, we met the time dilation formula. This showed that the time in an inertial frame of reference of a stationary observer is dilated relative to the inertial frame of a moving observer. In today's lesson, we'll meet a similar idea. This is that the length measured by a stationary observer is contracted relative to the length measured by a moving observer. For example, imagine two observers on a train. One of them, Mavis, is moving with a ruler. The other, Stanley, is standing on the platform. In her reference frame, Mavis measures distance L0 parallel to the direction of travel. However, Stanley would only measure a distance L for the same distance, where L is shorter than L0. The equation which describes this can again be derived by imagining a light clock moving along. However, a full derivation is again not required, so I'll leave this as an exercise for the viewer and will link to a derivation in the comments. I would also suggest that you get some practice using this equation, and so I'll link to some questions again in the comments. Further to this, we also need to understand the equation for relativistic mass. You may recall the idea of rest mass. The rest mass, m0, is the mass an object has when it is stationary. This equation states that the mass of an object m, the relativistic mass, increases as the speed of an object increases. You may also recall the equation E equals mc squared. This allows us to define a relativistic energy E equal to m0, the relativistic mass, times c squared, the speed of light squared, divided by the factor root 1 minus v over c squared. This leads us to a very important distinction between Einstein's theories and older Newtonian theories. For example, in a classical or Newtonian theory, the energy of the particle is equal to half times the mass times the velocity squared. In Newton's theory, the speed of an object will continue to rise indefinitely, that is, without any limit. However, in Einstein's theorem, there is a universal speed limit which applies to all objects with mass. This speed limit is the speed of light. Imagine, for example, you place a speed v greater than c into the equation. The root of the bottom of the equation would be negative, which of course doesn't exist on the real number line. In Einstein's theory, the kinetic energy becomes infinite as v approaches c. Another way of saying this is that you would need an infinite amount of energy to accelerate an object with mass to a speed c. This is closely related to our idea of a relativistic mass. It's best not to think of objects as getting bigger as they get accelerated. Think back to Newton's equations and ideas there about inertial mass. Inertial mass is the resistance of an object to being accelerated. This way of viewing mass is still correct in Einstein's formulation. In special relativity, objects become more difficult to accelerate as they reach higher speeds. That is, as you go to higher and higher speeds, close to the speed of light, you need more and more energy to further accelerate the mass. In fact, once you reach close to the speed of light, you would need an infinite amount of energy to accelerate the object to the speed of light. These ideas around relativistic mass were finally verified by Bertozzi's experiments. These experiments were performed in the 1960s to verify Einstein's ideas. To give you a very quick setup, we have a beam of electrons accelerated to a very high speed, which are then shot towards an aluminium disc. They are then allowed to collide with the aluminium disc. We can measure the speed of the electrons in the experiment by taking the time it takes them to reach the disc. The energy of those electrons can also be measured by measuring the temperature rise of the aluminium disc, assuming all of the kinetic energy of the electrons is transferred to thermal energy inside the disk. This was found to experimentally confirm Einstein's prediction. By plotting the energy of the electrons against the speed of the electrons, Bertozzi found a curve which very closely matched Einstein's prediction. This is the end of the Turning Points chapter of Special Relativity, and indeed the end of the course. Good luck.